Hi. So some students came up to me and asked me how to do volumes by shells. This is chapter 6, section 3 on page 433 using the James Stewart book right over here. The James Stewart book is used in colleges as well as most high schools now for the single variable anyways. They usually use it for multivariate calculus too. But for now, we're going to be using just the single variable calculus stuff. Okay, so let's get started a little bit. On page 634, I'm going to show you how that's done a little bit. So we're going to think about this. We talked about this right over here. And this is kind of like a soup can, okay? And it has a cut a little bit with the soup can. I'm going to cut it right down the middle here. And it's got a little bit of thickness called dx. So what I'm going to do is I'm going to do this. I'm going to cut it open like this. And then I'm going to kind of open it up again. And then do it more. And so you notice how it's like cut up open just a little bit with the change of delta x right there. And open it up fully. And it's going to look something like this now. And this is a rectangle. The thickness of this is delta x, or dx for short, or it could be delta y, change in y, or dy, okay, depending on how you revolve that, right? And looking at this a little bit, seeing how it opens up that soup can label, this is the length, which happens to be this length, which happens to be the circumference. So length is equal to 2 pi r. And then what's the height? We're just going to call it h. Alright, GHT is equal to h right there. There's h. That's 2 pi r, and that's delta x. And that gives it volume. So that's the volume of this rectangular solid that was opened up using the shell method. So how does it actually work? It's a little bit tricky, so I'm going to show you how it works a little bit here with this book. And this is on page 434. So here it is right over here. This problem looks like this. You got an inner shell, you got a second inner shell, and you're adding up all of these shells that's coming up. And so the thickness, as you revolve this around the y-axis, it's got a little delta x. That's how you chop up these shells. So that's your delta x right there. Okay. And so what's the formula? Volume is equal to the sum of the length, which is 2 pi r, times the width, which is, I'm just going to call that width, which is delta x for now, and then times it by the height. That's length times width times height. Okay. And that's the formula. Of course, we're going to factor out 2 pi. And we integrate it from the inner to the outer of the radius times h times dx. This is revolving around the y-axis. So you use delta x here. I'm going to use a different color pen. If it's revolved around the y-axis like this, you can use delta x. Obviously, if it's revolved around the x-axis, it's going to be change in y. We're going to add them all up, and that's what we do for the volume. Okay. So let's start a problem, example number 1, let's say. I don't have enough space, I'm going to use a different paper. It says, what color shall I use? This is on page 434, example 1. Okay, you're going to find the volume of the solid obtained by rotating about the y-axis, the region bounded by y equals 2x squared minus x cubed, and the line y equals 0. What kind of line is y equals 0? It's a horizontal axis. Well, let's see what this graph looks like. It's cubic in nature, so the degree is 3. When we factor out x squared, we end up with 2 minus x equals 0. So x equals 0 is a double root. X equals 2 is a single root. and this cubic is negative, so it's going to start lower, so it's going something like this. And then we're going to revolve it around the y-axis this way. Okay, and of course this is 0 to 2, y equals 0, and so we're going to, as we revolve it, it's going to be something like this now. You see that? Okay. Well, we're going to take a little strip of this right there. As we revolve it, it's going to go to this little strip right there. And what we happen to make is a cylinder. So that's where the cylinder comes in. So we start with the inner, we add up all to the outer. So what we do is, let's try this again. The volume is equal to 2 pi, from A to B. The radius happens to be the x direction. From here to here is the x, right? That's the radius. So it's x times the height happens to be f of x, or the y value, times dx, the little increments of the cylinder shells that we're making. So that's actually the concept right there. So here's the easy way to do that. Volume equals 2 pi integration from A, which is the inner, starting at 0, all the way up to 2, of x times f of x happens to be that, 2x squared minus x cubed dx. And we got a function as one variable. You should be able to do this without any trouble. This should be relatively easy to integrate. Any questions, let me know. And we're done, etc. Okay? Well, good luck on your homework, and let me know if you have any questions. Thanks. Bye.